Welcome back. We're going to continue our discussion on stoichiometry. And as I said in the previous video, you should already be familiar with most of the terms that leads into this concept, but the only new term that I mentioned in my previous video is the concept of mole ratio. Okay, now this is what actually ties in or connects just the concept of balancing equations to really make sense of the idea of law of conservation of mass, and you can actually predict how much product you can expect if you were to do a certain reaction. Okay, now let's go ahead and write the equation that we had earlier in the previous video, and that would be iron 3 oxide reacting with aluminum, making aluminum oxide and iron. And if you remember, I did had 2 parts of aluminum here and 2 parts of iron. Now, as I said repeatedly, I will probably never give you an equation that's already balanced. So it's your job to actually balance the chemical equation in the first place. So let's look at a problem, see how it makes sense. Now, this is the thermite reaction I demonstrated in class, right? So I started with certain amount of, say, iron oxide and certain amount of aluminum. So let's say I start with 3.5 grams of iron oxide, which is Fe2O3, and say 1.5 grams of aluminum. Okay. If this is exactly the proportion that was in that little ceramic, what do you call it, flower pot that I had, and I had used magnesium to light the whole reaction, and then it went really quick, and we made iron in the process, and whatever was left would be probably some unreacted of one of the reactants and one of the other products. All right, and if I ask you how much usually in terms of when you deal with gram refers to mass, so mass of iron would be produced. Okay, now this is something I have shown you in class, so it will be easy to understand what I'm referring to here. So if this is exactly the amounts I've mixed, then there's something called a theoretical yield. Let's write that down. Theoretical yield. Okay, that is, even before you actually commence the reaction, then you can anticipate or predict or speculate how much of one of the products or both of the products or however many products you have can be produced. Okay, so that is called theoretical yield. Now, would you always end up getting what you predicted? The answer is no. Typically, what you get is usually less or much less than what you expect will make. And what you actually get is the actual yield. And some people also write it as experimental yield. Both are correct. Neither one is right or neither one is better than the other. It's really up to you. Whichever one you want to remember, you can remember that. All right, so this is what you speculate. Okay, well, you make of a particular product. This is what you actually obtain. Okay, so we will learn the concept of percent yield, but let's get back to the problem that we have at hand. But I want you to be familiar with these 2 terms. All right, so to get started with the problem, you're given mass of 2 separate reactants, right? Treat them both as 2 separate information and treat them as a given information like we have done. So that's 1, okay? And then iron oxide, I believe iron is 56. So 56 times 2 plus 48. So 160 grams over 1 mole. Now, whenever you're trying to use the idea of mole ratio, which I'm going to write it in different color, it will go in this column. Okay, this is the sequence. Mole ratio cannot be thrown in until you actually calculated the moles. You cannot go from grams to moles through mole ratio without actually going through moles of that substance first. Okay. All right. So now keep in mind, this is for the iron oxide, right? But we're asking how much of iron would be produced. So first, what we want to figure out is the moles of iron from two separate perspectives. So it's 3.5 over 160. But then the amount of moles that's produced is dictated by one of the two, not both, but one of the two. We have to figure out which one before we can actually obtain the mass of iron that will be produced. Okay. Now, what's the ratio of iron oxide to iron? This is what we are trying to understand. Okay. For every 1 part of, I'm going to write 1 here. For every 1 part of iron oxide, 2 parts of iron will be produced, right? So, excuse me. So for 1 parts of iron oxide, you produce 2 parts of iron, right? So that means if you get rid of grams, you would actually be left with moles of iron. Again, why do we put the iron on the top? Because that's what we're trying to figure out is the mass of iron. Okay, let's stop right here and then go to the second piece of information, which I'm going to write it in again a different color so you can see. So we're starting with 1.5 grams of aluminum. And again, that's your given information. Okay. So write 1 below. Again, aluminum is 27. So it's 27 grams over 1 mole. Okay. Now again, we use, this column right here, the third column that we have is the mole ratio. Okay. Now if we compare aluminum to iron, we're basically only asked to figure out mass of one of the products. So we compared this with that. Now we're comparing this with that. Okay. So for every 2 parts of aluminum that you start with, you produce 2 parts of iron. Okay, keep in mind to write Al here so you know which ones you're canceling. So you also end up with moles of iron here. You can write 2 moles of iron or just 2 parts of iron over 1 parts of iron oxide. They're both the same. And because this is technically moles, right? 1 mole of iron oxide reacts to produce 2 moles of iron. And I'm going to do the same here in blue so you can see difference. 2 moles of aluminum and 2 moles of iron. Okay. So now let's actually calculate these 2 numbers. Why are we doing this? Because we need to know where do you produce the least moles, and that's usually, remember I said only one of the 2 dictates how much iron you will produce. Okay, so that's the top one is 0.0453 and the bottom is 0.055. Now you do this to figure out the actual reactant that controls how much of iron will be produced. So you do 2 separate calculations and then you determine which one of the 2 numbers is small. Okay, I see that this is small. So where did this number come from? It comes from starting with iron oxide as my reactant, right? So smallest wins the race. Okay, the lowest of the 2 numbers. Lowest of the 2 numbers wins the race. Okay. So that means what is our limiting reactant? I'm going to write this in another color, maybe orange. Okay. What is the limiting reactant? Iron oxide is my limiting reactant. Means it's what controls out of, we have two reactants, both of them cannot be limiting or both of them cannot be excess. One of them is limiting, one of them is excess, and we can only determine that based on the actual calculation, not by looking at one or two. Sometimes it does work, but most of the time it may not work. You cannot ever judge whether it's limiting or excess based on whether it's one or two or one. You have to actually work out the calculation. That means this right here is your limiting reactant number. Now, how do we actually complete the problem? Let's go get another color. Actually, red might work. Okay. We start with the information we calculated as our given information now. Okay, as your given information, so 1 goes here. We are trying to find the mass of iron, so we already know the mole. So if you just put the molar mass of iron, which I believe is 56 grams over 1 mole. Now, if this were a compound, then you determine the molar mass of that. But here it's just iron, so it's 56. So it's 0.043 times 56. So that's 2.408 grams. This is the theoretical yield. Means before you actually commence the reaction or the demonstration that I did, if I want to know how much of that iron piece I would get, then this is exactly what I would do, so I can get 2 grams of iron in the process. Okay, now how do we calculate the actual percent yield? Let's finish this over here so we don't need to open another video just for this. So what is let me go get another color. So we said the iron oxide, one of the two reactant, is limiting. So what does the aluminum become then? It's called excess. Okay, one is limiting, the other is excess. If you have 10 reactants, there can only be one that's limiting. That means the remaining is all excess. Okay, that means, remember when I did the demonstration, we got piece of iron in the sand, but then there were also some residue sticking around it in the sand and was on the iron piece itself, and it was sticking to the pot and everything. There's probably some unreacted aluminum, and probably some aluminum oxide is also there because that's another product that's formed. Okay, so how do we calculate the percent yield? Well, we can't calculate that because this is theoretical yield. Let's say, let me actually write the question a different way now. Actually, it was not part of the original question, but I'm going to add an appendix to it. Let's say you actually made the actual yield was, remember the way we did it in class was not the most efficient way to make iron. There's probably other ways you can make it. The actual yield was, say, 1.5 grams. Okay. Then what is the percent yield? That would be actual yield or experimental yield over theoretical times 100%. Okay, that means your actual yield is 1.5 grams, your theoretical yield is 2.408 grams times 100%, which would be 1.5 over 2.408 times 100. So about 63%. Okay, so we will, just one problem is enough because I focused this time on iron. Just do, let me actually write the question in a separate video. So 63%. Okay, so only one of the reactants can always be contributing as limiting because it controls how much of iron you would actually make, and then how much of aluminum oxide will be made too. We haven't looked at that. We only always focus on one or two reactants. In this case, I just focused on only one of them. All right, so let's say I'll leave you with this question in this video before I go to something else. is. All right, so I'm going to give you that same equation. So it's iron oxide plus aluminum going to iron plus aluminum oxide. Okay, if you start with 3.5 grams of iron 2 oxide and 1.5 grams of aluminum, how much in mass usually refers to the theoretical yield, how much of Al2O3 will be produced? Well, you don't change anything with the process. You still have to calculate the moles just like the mole rate, using the mole ratio just like we did. Okay, and then I'm going to add if the actual yield was, say, 0.5 grams, what is the percent yield? So there's two parts to this question. Okay, what is the percent yield? Now I'm going to work this problem out, but I highly recommend you stop the video at this point, work it out, and then come back and play and see if you got it right. If not, write down exactly what part of the problem you're lost or you got it wrong. Only then it's easy for you to fix that one mistake, and then you can be on your way to get the problem right. All right. Assuming you have worked out the problem, here's what it looks like. So we first balance the equation before we proceed. Okay. So I'm starting with 3.5 grams of iron oxide, right? And that's my given information. Like I said, you treat each of the given masses as two separate given informations. And I think we did that in the earlier screen. It's 56 times 2 plus 48. I believe it's 160 grams over mole. And this is where you use the mole ratio. So I'm going to write that in different color, perhaps a pink. So this is iron oxide, right? So whatever parts of, if there is no number, that means you assume it's 1, right? You don't need to assume, it is 1. So for 1 mole of iron oxide or 1 part of iron oxide, you produce 1 part of aluminum oxide, right? That's what we're interested. And then we just say, this is moles, by the way. So just leave moles of Al2O3, because if you see, just about everything cancels out, right? I'm going to get a light color just so I can cancel grams, grams, moles, and moles. We're left with moles of Al2O3. So let's go do the same with the second piece of information. So it's 1.5 grams of Al over 1. And then aluminum, I said was 27 grams over 1 mole. This is aluminum, right? Again, mole ratio is for 2 parts of aluminum. See, the reason I said you would like it is because we're going from reactants to products. Reactants always go on the denominator because you're moving in the forward direction. And then we're looking at moles of aluminum oxide. So that also will leave you with 2 separate values of moles of Al2O3. Okay, so you can cancel out grams, moles of Al. We're left with this. So let's calculate the moles for the 2 separate numbers. So 3.5 over 160. So that will be 0.0218. And I'm going to write this in a different color so you can see the difference. So it's 1.5 over 27 over 2. So it's 0.0277 or 7. Which of these 2 numbers is the smallest? I said the lowest number wins the race. So this wins the race. So that means this is my limiting reactant is, where do we get this number from? What reactant did we start with? It's iron oxide. And what is my excess? This is my excess, which comes from Al. So excess is Al, limiting reactant is iron oxide. So now to actually figure out the physical amount of aluminum oxide, we take the 0.0218 moles divide by 1, and that's again aluminum oxide's formula. So if we calculate the molar mass, I believe is 27 times 2 plus 48. It's 102 grams over 1 mole. Moles cancel out. So times 0.0218 would be 2.22 grams. This right here, folks, is the theoretical yield or speculated yield, not what you actually got. This is what you can expect the most if everything works right. Just like no engine is 100% efficient, no reaction can lead to 100% of the theoretical yield that's expected. All right, so how do we actually calculate the percent yield? Percent yield is actual over theoretical and times 100%. So actual yield was 0.5 gram and the theoretical yield was 2.22 grams times 100%, and that would be 0.5 over 2.22 times 100%. It's about 22.5% or 23%, however you want to write it. Okay. Now, if you see something very interesting, let's say if you round this off to say 23. Okay. I believe in the previous video, we got around 67% for the iron. Okay. This is the theoretical yield for 67% is iron, 23% is aluminum oxide. Now, if you see, you add up to 100%. Typically, these numbers should add up to 100% if you do two separate calculations to figure out the theoretical field for each. They both should add up to 100%. So if you start with 100% reactants, you end up with 100% products. How much of each of that is the key here? You see, they're not equal. What people say equal is these numbers are equal. Rarely that's the case. Okay, usually each of the reactants and products will be in different percentages. If you put everything equal, you would still get different amounts of products. Okay, so this is all I really want to say to drive this concept. So I'm going to stop this video. When I come back, we're going to look at the idea of stoichiometry for solutions. Right now we looked at solids. Okay, you saw that demonstration that I did. There was no liquid in it. It was just pure solid. So how does this concept of mole ratio and stoichiometry carries over to something that's in a liquid form or even, for that matter, a gaseous form? All right, so continue to watch these two videos. Okay, and I'll be back with another video. Stay tuned. Bye-bye.